probes for the prediction of therapeutic effects of EGFR tyrosine kinase inhibitors. In this presentation, I divide into two chapters. The first one is a synthesis and evaluation of 125 iodine ICO1686 as a spec probe for lung cancer with L858R T790M EGFR mutations. And the second one is 77-bromine PRCO1686 preclinical evaluation as a PET probe for lung cancer with double mutations L858R T790M. Next, introduction. Despite the continuous development of cancer treatment, lung cancer remains a deeply disease worldwide, and we can see for both male and females, lung cancer is accounting for over 20% cases in 2020. And the non-small cell lung cancer, and SCLC, is the most common lung cancer, accounting for over 80% of all diagnoses. And the mutation in the exon 18 to 21 of EGFR has been associated with an SCLC. And the single mutation, EGFR L858R and exon 19 deletion, are frequently occurring mutations. Actually, the treatment of an SCLC patient by EGFR tyrosine kinase inhibitors by first and second generation EGFR have shown impressive therapeutic outcome, like gefitinib and also erlotinib. And first and second generation tyrosine kinase inhibitor shown prolonged the overall survival of an SCLC patient with EGFR L858R and exon 19 deletion. However, most patients acquire further mutation, and EGFR L858R T790M mutation was found as the mutation of EGFR, and it eventually develops drug resistance. Therefore, some third-generation tyrosine kinase inhibitors were developed, such as ruxolitinib, CO1686. Third-generation tyrosine kinase inhibitor, ruxolitinib, is potent toward EGFR L858R and exon 19 deletion. It is aminopyrimidine-based molecule, and also the affinity of this drug, because of the trifluoromethyl moiety here, and will interact with the kinase of GFR domain by hydrophobic binding. Therefore, CO1686 is a prominent EGFR tyrosine kinase inhibitors as best structure to develop a molecular probe for detecting mutation of EGFR. So in this study, I aim to radio label of this compound by iodine and bromine to monitoring the mutation of EGFR. Diagnostic method. Currently, the common strategy to monitor the mutation of EGFR double mutation is biopsy, like gene sequencing and immunohistochemistry. However, because of the tumor tissue are heterogeneous, the biopsy doesn't necessarily reflect complete tumor mutation, and also the tiny fraction of biopsy might not be representative of whole tumor profile. Additionally, repeated biopsies are invasive and also burden on patient. Therefore, revolutionary invention in the diagnostic field, it is nuclear medicine imaging using PET or SPECT modality. It has a greater ability to determine the expression level of target molecules and also they are non-invasive on patient. Nuclear medicine imaging. Once the radio tracer accumulates in the body, the radioactivity of the radio tracer will be detected by PET or SPECT scanner, positron emission tomography, and also single photon emission computed tomography. And the scanner will obtain information about physiological, cellular, and also molecular process by three-dimensional images like this. So we can see the position of cancer and also can determine whether this cancer sensitive toward the therapy or not. So we can choose the appropriate therapy for this cancer. Next, radio tracer. Actually, there are some radio tracer based on the third generation EGFR tyrosine kinase, such as carbon-11 osimertinib. However, this radio tracer only to display brain penetration of tyrosine kinase inhibitor in a preclinical setting. And this radio tracer not designed for selection of sensitive patient to the therapy. Therefore, I aim to develop a radio label probe from the third generation ruxolitinib to monitoring the mutation of EGFR for selection sensitive patient to the therapy. Chapter 1, Synthesis and Evaluation of 125 iodine ICO1686 as a SPECT probe for lung cancer with L858R T79M T790M EGFR mutation. And in this chapter, I would like to explain I synthesize this compound by introducing iodine in this position, and I would like to show you the effect after I introduce the iodine in this position. Drug design. CO1686 has three important molecules in this structure. The first one is the aminopyrimidine group. The aminopyrimidine group will form two hydrogen bonds toward the kinase, especially M793, and also the second one is the methoxyl substituent play a key role in the superior selectivity toward EGFR mutation, and the third one is the trifluoromethyl in this position will be bind toward M790 by hydrophobic binding. Therefore, I would like to introduce the iodine in this position because I expect that when I introduce iodine in this position could not influence the activity of parent compound CO1686. The next is a SPECT imaging probe. I would like to explain the SPECT modality. SPECT, a single photon emission computed tomography, is a medical imaging technique that is based on the conventional nuclear medicine imaging and tomographic reconstruction methods. The image reflects functional information about patients. SPECT differs from the X-ray tomography. The X-ray tomography, instead of outside of radioactivity of patient, but for SPECT will identify the radioactivity inside of patient. And what is the advantage of SPECT? The first is the half-life for many SPECT radionuclides are longer than PET modality. And the next is radio tracer do not require relatively close to a medical cyclotron because of the longer half-life or radioactive life. And the third is the system are lower cost and have a much installed worldwide. SPEC imaging probe with iodine 123 is the common use for synthesized radio imaging probe for SPEC because of the half-life 13 hours. It's enough for providing experiment. However, in this study, I use 125 iodine as an alternative for 123 iodine because of the half-life much longer than 123 iodine, and it is convenient for me to do preclinical study. And the radio label compound, I will introduce the 125 in this position to provide 125 iodine ICO 1686. The next, it is the synthesis scheme how to provide the ICO 1686. I synthesize this compound by multi-step reaction from the commercially starting materials, and I follow the previous study with a slight modification. And in this case, I divide into two fragments. The first one is a synthesis of compound 5, and the second one is synthesis of compound 9. After that, I conjugated the compound 5 and 9 to produce the final product, ICO 1686, with high yield, around 73%. Next, cytotoxicity of ICO 1686. In this study, I use 3 human lung cancer cell lines with a different type of mutation. The first one is H1975, correspond to the double mutation of EGFR. The second one is H3255, correspond to the single mutation EGFR, L858R. And the last one is H441 as a wild type. Based on this result, we can say that the iodine substituent in this position doesn't influence the activity of parent compound, because when we compare between the iodinated compound and non-iodinated compound, the IC50 looks comparable. And then the activity of gefitinib, we can say not active toward the double mutation of EGFR, and also not active toward wild type EGFR, but high activity toward single mutation of EGFR, because gefitinib has high sensitivity toward single mutation EGFR as a first generation tyrosine kinase inhibitors. Besides this, the introduction of iodine in this position slightly influenced the activity of CO1686 toward H441. Why? Maybe because of the introducing of iodine. But in this case, it is not important because ICO 1686 was designed to inhibit the H1975 as double mutation of EGFR. Next, radiosynthesis of 125 iodine 10. A precursor 11 was prepared by palladium catalyzed stannylation reaction of 10, and I got 10% yield after purification by HPLC. After that, I synthesized of radiolabeled compound 12510 by an iodo-destannylation reaction with the corresponding tributyltin precursor. 11 with high radiochemical yield around 77% and high purity over than 99%. And the next is analysis of radiotracer. I would like to confirm that the product is my desired product, so I should confirm the retention time between the radioactive compound and the non-radioactive compound. And we can see the retention time of radioactive compound was identical to that of non-radioactive compound 10 in the HPLC analysis. So I can confirm that the product is my target product. The next is a partition coefficient. After I got the radiolabeled compound, I also performed the experiment partition coefficient to determine the polarity of the radiotracer. The radiotracer was mixed between the organic layer and also the aqueous layer. After centrifugation and also separation, I measure respectively into the gamma counter. And after I calculate the fit log P value, I found that the radiotracer 125 iodine, the log P is 1.84. The next is stability of 125 iodine 10. As we can see in this graph, 125 iodine 10 was stable in the PBS and also plasma, because we can see the radiotracer was intact over than 90% after 1 hour incubation at 37 degrees Celsius. And also the reactivity decreased to 80% after 24-hour incubation. Next, a cell uptake of radiolabeled compound iodine 125. In this study, I used a stem human lung cancer cell line as the cytotoxicity assay. H1975 correspond to the double mutation EGFR as my target cancer cell lines. And the second one is H3255 is a single mutation EGFR. And the last one is a wild type. And we can see the highest uptake of radiotracer was in the H1975. And also, when I use the blocking agent, rosiletinib, the uptake of radiotracer dramatically decreased. In contrast, when I use gefitinib as a blocking agent, the radioactive compound cannot be decreased by gefitinib. Yeah, of course, because gefitinib is not sensitive to our H1975 as a double mutation EGFR. And also we can see the uptake in H3255 not so high because of H3255, the binding position of H3255 is not suitable toward radiotracer 12510. And when I use gefitinib as a blocking agent for H3255, the radioactive compound significantly decreased. And the last one is H441, and we can see there is no change, and also the radioactivity significantly lower than other cells. Next, a biodistribution in the normal mice. In this graph, we can see the uptake in stomach was low, indicating that this radiotracer hardly decomposed to free iodine. As we know that free iodine will be accumulated in the stomach, and in this case, the accumulation of radio-labeled compound in the stomach not so high, so I can confirm that the stability of radioactive compound is good. The next is the accumulation in the liver and small intestine and also large intestine were the highest one than other tissues. The high uptake in the liver was caused by the relatively hydrophobic structure of radiotracer compound with the log P 1.84. The high uptake in the liver and intestine is consistent with the previous report with carbon-11 label CO1686. Liver activity decreased gradually, and the radiotracer was transferred to the small intestine via bile excretion, and finally this radiotracer was excreted by feces after 24 hours post-injection, and almost 70% excrete. Namely, 125 iodine 10 was mainly eliminated through hepatobiliary excretion. The next is the biodistribution in tumor mice. The highest uptake looks similar with the normal mice, the pattern. The highest uptake were in the liver, intestine, small intestine, and large intestine. At first, I would like to introduce how to prepare the cancer cell line. The tumor-bearing mice were prepared by implanted subcutaneously of H1975 and H3255 in the left and right side of mice, respectively. And after 2 and 3 weeks, the tumor will be palpable size and the mice ready to sacrifice. The unblock of blocking agent in the uptake of radiotracer in tumor looks not so high, and also comparable between the H1975 and H3255. And the blocking agent could not reduce the uptake of radiotracer due to the non-specific uptake in the tumor region. So, improving the water solubility may be necessary to improve the accumulation of radiotracer 125 iodine. Conclusion: 125 iodine label ICO1686 was synthesized in high radiochemical yield and purity, and also this radiotracer has high specificity toward EGFR L858R T790 mutation in vitro, and also to optimize the intratumoral uptake, reducing the lipophilicity by replacement of radioiodine with radiobromine would be possible approach. So the next chapter, I aim to radio-label compound CO1686 using bromine 77. Drug design looks similar with the iodine compound because we know that iodine is isosteric of bromine. So when I change the position of iodine to bromine, it could not influence the affinity of this compound. In this study, I aim to provide PET imaging probe. So There are two reasons why I choose the bromine compound. The first one is to reduce the lipophilicity and increase a little bit the hydrophilicity. And also the bromine radionuclide is designed to provide the PET imaging probe. Because the PET modality offers higher resolution over conventional specs and also a low quantification of radioactivity with high accuracy. In this study, I used 77 bromine as an alternative of radiobromine 76 because of the longer half-life, so it's convenient for me to do preclinical study. And this is the synthesis scheme of radiobromine compound. At first, I should synthesize the brominated compound, non-radioactive, and I synthesize by multi-step reactions from the commercially starting materials. And I follow the previous study by slight modification. And the cytotoxicity of bromine compound looks comparable with the iodinated compound and also non-iodinated compound. And the same cell lines, H1975 as a human lung cancer double mutation EGFR, and H3255 as single mutation, and H441 as wild type. So I can say that the bromine substituent in this position does not change the activity. The next is the radiosynthesis. So the bromine compound was synthesized by bromodestanylation reaction with the corresponding tributyltin precursor, same as the iodinated compound, with moderate radiochemical yield around 45% and high purity over 99%. And also I confirm whether this radio tracer is my desired compound or not. So I confirm the retention time between the radioactive compound and non-radioactive compound. And we can see the retention time of both compounds were identical in the HPLC analysis. And the partition coefficient of bromine compound was 1.72. It looks little lower than iodinated compound, and also the result was supported by the retention time of radiobromine compound come earlier than retention time of radioiodinated compound. And the stability of bromine compound looks not so high stable than iodine compound because the radio tracer was intact over than 80% in the PBS and murine plasma after 1 hour incubation, and its purity decreased to 57% after 24-hour incubation. And the cellular uptake study show us a similar pattern with the iodinated compound, with the highest uptake in H1975 and dramatically decreased by pre-treatment of ruxolitinib. And the biodistribution in normal mice, we can see high uptake in the liver and small intestine, similar with the iodine compound, but in this case, the retain of a bromine compound looks longer than iodine compound. And finally, only 30% bromine compound was excreted by feces. And the tumor biodistribution in tumor mice show us high uptake in the blood and also high uptake in the tumor compared to that of iodine compound. However, the ratio tumor to blood between bromine compound and iodine compound, the bromine compound looks lower than iodine compound. And it is the biodistribution of free bromine. because I think why the blood accumulation of bromine compound was high due to the free bromide of radiolabeled bromine compound. So I confirmed by biodistribution of free bromide into the mice. And we can see the biodistribution after 24 hours looks retained for a long time. So the conclusion, radiotracer 77 bromine 17 show high in vitro specificity toward NSCLC cells with EGFR L858R T790A mutations, and the structural modification by introducing hydrophilic group such as polyethylene glycol in the linker phenyl would be possible approach to optimize the uptake in tumor. Thank you.
Thank you for your presentation for us. それでは草野先生またよろしくお願いします。
So finally, so you mentioned that the necessary of the structure modification of the about the IC0686. So can you explain the structure modification using the X-ray analysis? Okay. So I understand that you show the substitution of the pen.
Yes.
But so I'm sure. So please can you say the future plan using the X-ray analysis? Please show the X-ray analysis. And the binding model. Yes.
Thank you for your question. In this case, my compound, the uptake in the tumor is not so good. I think because of the high lipophilicity, so the permeability towards in the cell is not so good. So I plan to introduce PEG in this position. To increase the hydrophilicity of my compound, and I can say that in this position could not influence the activity of this compound because the target binding position of this compound should be in this position, hydrophilic bonding, and also in this position hydrophobic interaction toward M790 in the kinase domain.
So you mean the hydrophobic interaction is important?
Yes. In this molecule, hydrophobic interaction is important because
I know, understand the trihydromethyl group is and methoxy group is critical for the hydrophobic environment. So, okay, so which position introducing the pair?
I plan to introduce here.
How many numbers the tethers?
Not so, maybe 2 or 3.
2 or why?
Yes.
Why 2? Why 2?
Because I think that the log P of this compound not so high, around 1.8. So just short linker of PEG can reduce a little bit of the hydrophobicity. Because if the longer linker of PEG, it could be decrease much more the lipophilicity of my compound, and it is not good for my compound.
So that is X-ray analysis. This is calculation model. X-ray analysis.
Yes, Sensei.
X-ray.
X-ray analysis. Crystal structure analysis.
Crystal structure.
Yes.
Okay, so you know the electron density is this model. Electron density. You heard.
I don't know something about the electron density of this.
Just Excel.
Yes.
You have a calculation model?
No, sensei.
Okay, I know. So I'd like to know the electron density of this active site.
Electron density.
Never.
Never.
Okay, so trifluoromethyl group is affected over hydrophobic interaction, right? Hydrophobic binding.
Hydrophobic binding.
Okay.
Thank you, sensei.
Thank you for your presentation. I think you did a good job. And I have a similar question with Dr. Olivia. You said this is a X-ray crystal model, binding model, right? In that case, this binding site is same as eraser one or not? Because why I asked this one? That the activity is quite different between compound CO16-886 and yes. So I thought the binding site is different between both. And I'm asking you, this compound has the same binding site with yes or no?
Do you know yes?
Yes, sensei, definitely. Thank you, sensei. As far as I'm concerned about the tyrosine kinase inhibitors binding position between the IRSA and the CO1686, actually the binding position looks similar. But the problem is the mutation of in this position and in this position interfere the activity of ERASA. So that's why the activity of ERASA cannot be so good toward double mutation.
Okay, I understand. Thank you.
Hey.
And another question related to this compound, this one. Sorry, I can see the rest. It seems not to correlate between the data of the cytotoxicity and the uptake data. This is why it's happening. I think you explained about the hydrophobicity, the difference of hydrophobicity can make this difference. But I think another reason may have.
Do you mean the cytotoxicity affect not correlate with the uptake?
Uptake data, and also the uptake data is not correlated with the distribution data.
Okay.
So why do you have any idea of this reason?
Hi, thank you for your question, Sensei. I'm searching about the reason why sometimes the cytotoxicity effect is not correlated with the uptake. Some studies show also different. In this case, I think because the cytotoxicity, the first reason is the treatment of compound in the cytotoxicity assay. It is for 2 days, two days, twice of 24 hours. And then in the biodistribution, the cell uptake study, I incubate the compound only for 4 hours. So it's quite different method and also the time of incubation. And the second reason is the efflux transport of cell. Some cells correspond to the PGP will efflux of the uptake of not only radio tracer but cancer drug. So when they uptake and also they will efflux again outside outside the cell. Right. And also the biodistribution uptake is not correlated with the cellular uptake. I think the first reason is the high lipophilicity was related to the high hepatobiliary clearance of this compound. So this compound has not enough time to accumulate in the body, in the targeted tumor, because of high rate of hepatobiliary clearance. And the second one, maybe because of the non-specific uptake of radio tracer, resulting in the blocking agent could not decrease the uptake in the tumor, targeted tumor.
In the cytotoxicity data, the data of the cytotoxicity, this is you mean that in this data, the PGP or other efflux form doesn't work?
Maybe it's work.
Oh,
Yes, because of it is the mutation cell, and some mutation cell activate the PGP or BRCP.
Yeah. I thought from this cytotoxicity, the data of the cytotoxicity, the data uptake should be more high for it's 30 to 55.
Yes.
The value of it's 30 to 55 should be more high from the cytotoxicity data.
Yes.
So you explain about the PGP or like that for this reason?
Yes, I want to. I try to understand what you mean. You mean that the cytotoxicity of this compound looks high, or correspond to the IC50 looks similar, but the uptake is not so good in this. So maybe the efflux mechanism of this H3255. So when they uptake and also they will efflux again.
In case of this
Yes, in case of this study.
but you incubate only 4 hours.
And also I only incubate for 4 hours.
EGFR の活電量も違うので、最後の動作になってくるので、ちょっと単純にはできないかなと思います。もう今の
Thank you for your presentation. I have a similar question about the biodistribution of this compound. So, your drug design is based on the known compounds about the parents compound. I mean the not solid. Yeah, this one. So are there data for the lipophilicity of this compound? I mean the log P value.
Yes, Sensei. I also think about that, and I'm looking for about the log P data, but I could not find the log P data of fertility.
So, do you think the log P value is similar to the your synthesized compound as this one?
I think a similar value based on the biodistribution data of carbon 11 of CO1686 looks similar, highest uptake in the liver and also in intestine. So I think the similar hepatobiliary clearance process.
So in this case, I think the metabolism is biodistribution is very so. I mean, how do you change the biodistribution for the target issues to use this compound? Because the CO1686 is similar to your compound as in the biodistribution, but if you use the radioisotope compound, I think the distribution have to accumulate in the target issues. Only target issue, I mean the lung cells or lung carcinoma. How did you change the distribution using this compound, or do you have some other ideas to change the distribution?
Yes, thank you so much for your question, Sensei. The first strategy is change the radiohalogen from iodine to bromine, and it looks not so influence the uptake. And then I will introduce a short chain of PEG in this position. I expect that when I introduce the PEG, it could decrease a little bit the lipophilicity and increase a bit hydrophilicity, and it will be prolong the distribution into in the body.
In the body, but I mean that the
Target.
target tissue, how to accumulate in the target tissue, and do you have some other idea like a DDS or?
Maybe the next strategy, we apply the drug delivery system, as you say. For example, modify the surface of this compound and modify the surface by nanoparticles. And I think it's convenient for this drug to target into the tumor. I think. I think.
Thank you for your presentation. So first, I have similar question with what Osa said. So about so the drug target of this drug is tyrosine kinase domain of EGFR.
Yes.
So I think you should evaluate the affinity toward tyrosine kinase. What do you think? Have you ever tried, or you tried some approach using
The affinity.
affinity toward tyrosine kinase or inhibition activity toward tyrosine kinase?
Oh, I performed the cytotoxicity assay to confirm the affinity of tyrosine kinase like ICA, like rosiletinib and gefitinib.
So, as you said, cytotoxicity assay are not necessarily correlated with mutation. So, because your drug could cause other type of cytotoxic mechanism. So, to evaluate, so your drug as a diagnostic agent for the gene mutations. So you should evaluate the exact drug target, so affinity towards the exact target.
Oh, you mean the kinase assay?
Yeah, kinase assay, providing assay toward kinase.
Actually, a student already performed the kinase assay, and the result showed that this compound high affinity toward the kinase.
So,
I have no sense in it.
So what do you mean? So high affinity toward kinase. What kind of kinase? Mutant or wild type? Or so try for all of these three kind of kinase.
Yes, Sensei. We already tried for three types of mutation of kinase: double mutation, single mutation, and wild type.
And the highest inhibition activity toward double mutation.
Yes, Sensei.
Okay. And also, so you said so because your purpose is to detect the double mutation, that the cytotoxicity toward wild type is not so important, you said.
Yes.
I think it could be interesting because your purpose is to distinguish wild type and double mutation. It should not have high cytotoxicity or high affinity toward wild type. And so according to your research, so your drug exhibited lower affinity toward wild type compounds.
Yes.
Compared to original compound CO1686. I think you should more focus on the difference. So if you enhance the lower affinity property toward wild type, so it could enhance the contrast between wild type and double mutation. What do you think about it?
I think the result of cytotoxicity of between the iodinated compound and non-iodinated compound toward H-CoCo1, it is the convenience for me because when I introduce the iodine, it could difference cytotoxicity. So when we use this compound to distinguish patient, it could be useful. It could be useful to distinguish which patient sensitive toward CO1686 and which patient could not sensitive toward CO1686.
Okay. So I think so first you so the related part will not affect on the activity, but it actually affected on the activity toward wild type.
Yes.
So I basically agree with your answer. And the structural modification at that position could be promising, and in future you should more focus on the affinity of the position and how it could affect on the affinity toward wild type.
Thank you, Sensei. Yes, Sensei.
先生方よろしいですか。学生何か質問ありますか。 なければちょっとだけ早いですけど、ほぼ時間なんで終了させていただきたいと思います。佐野先生以外は退出お願いします。いや、ちょっと間違いについてリストアウトしてもらいます。先生方次ってこうあります？
次の次。
次の次。
僕は審査がないです。
後藤先生はいます。わかりました。先生後で部屋に。
あ、でも次の次なんで、その終わったらで次の次。
ちょっと今プリントアウトしてきていいですか？
あ、いいです。いいです。じゃあ、
名前をお願いします。
待ってます。いいです。
はい。